make this from that. So you see this carbonyl becomes alcohol and another part's added. So we can easily see that that's basically methyl green reagent comes in, makes an attack with the carbonyl, then you get an alcohol. So that basically is. So you got the methyl green reagents, and that makes an attack to this carbonyl. Then you get this. If you think about doing that, then definitely you are wrong. You don't realize that there is an aldehyde, it can also react. In fact, I told you the reactivity of the carbonyls. Aldehydes are more reactive than the ketone. So if you treat these two, this will react with that aldehyde first before you react with that. Maybe it can react both. So it could be the maybe first product it forms, but because of reactivity change differences are so small, it can probably react both, some unreacted, so it's going to be chaotic. So how can I do this? So basically, what you need to realize that we need a Grignard reaction with this carbonyl of a ketone, but this aldehyde is in the way. We have to kind of temporarily block the aldehyde. So that's the way you need to understand protective group strategy. Aldehyde can be formed the cyclic acetal, especially the aldehydes are more reactive than ketones. So if you're doing this thing, we're expecting the more reactive carbonyl will be used to make a ketal acetal first. We make an acetal with an aldehyde because it's more reactive than these carbonyl ketones. Then this one now, with no trouble for using Grignard, it will make an attack. You get the hydroxyl groups there, but we gotta break it up. So by breaking up the acetal, the mild acetic acid, this is different from the strong acetic acid. This is very mild, like 1 normal, even half normal is CL, and in water, that's what it needs. When you break up the acetal, you get the aldehydes back. So this is the kind of the things that I want you to remember. The protecting groups will make certain things possible if something is in the way, especially like this. All right, similar reactions. Let's think about how you're going to do this. You are making double bonds. Double bonds can be made many different ways. I mean, there are so many other ways to do this, but since we just learned the Wittig reaction, so let's try to use a Wittig reaction for this. But the thing is, in order to make a Wittig reaction, you can think about either these parts an aldehyde or that part's an aldehyde, either way, right? These double bonds here, these parts can be this part can be aldehyde or that part can be aldehyde. And I think these parts now that's much easier because we can always make a new profile there. So you are needing like the triphenylphosphine to replace the halogen and then pick out the proton from there. That's how to make a Wittig reagent, right? But once you do that, you should realize that if there is a carbonyl, it can basically self-react. So this is another problem of the protective groups. So that aldehyde must be coming from that side. Then if you have that, if you don't have this one, then of course it will react and you can make this. But the problem is this. So you need to protect this carbonyl. It just doesn't work this way because of that there. So what do we do? If you want to match the carbonyl of the ketone, you can make a cyclic acetal. The ethylene glycol or a little bit of acid will make a cyclic acetal. Now we don't have that complication. So you can basically do the same thing. Triphenylphosphine to replace the halogen, and then the deuterium to take the protons away. That will make a phosphorus ionate right now, like this. And use the same aldehyde we done. That will make a double bond between these two. And then once you get the form, then these acetal need to be broken. So that the protection can be done by just acidic work.